All right. Welcome to mass spectroscopy of elements. Now, a little bit throughout the difference of AP Classroom and the AP test, you learn about different instruments and how we're able to analyze things and kind of looking at that data to get information that isn't normally very direct. So mass spectrometer is our first area where we look at. So essentially a unknown amount or unknown substance is put in here. It ionizes it, which means it strips away electrons, gives things a charge. It goes through this mass analyzer, which is a area which has a magnetic field, and based upon how much it attracts or repels positives and negatives, it's going to make it move to the ion detector, which is going to put it in an area where it's going to hit further or closer based upon that mass to charge ratio. With that information, a little computing will help determine what its mass is likely to be. So many of this is used in order for comparisons to determine relative abundances. I read a whole interesting book over the summer about the history of how chemists, or what they called them back then as alchemists, were determining the different types of mass ratios, all based upon very challenging things. This makes it a lot easier today, and we use some vacuum pumps to make sure there's nothing else in here other than the ionized source, and that's it. So this really introduced the idea of what are called isotopes. Atoms, like all of iron, but have different number of neutrons. Why? Well, things form kind of randomly in the universe, and sometimes there's more options than just one. Some atoms only have one or two. Some have many, many different isotopes. But neutrons have different mass, so these different isotopes would pass through the mass spectrophotometer and create different amounts of these different isotopes. So there's nothing chemical or physical properties being different aside from mass. So they said, well, why do we care? Well, we need to think about this in the idea of mass and how many each thing actually weighs. So I gave an example, not related to chemistry, something you could probably relate to. So all oranges are different. So if I asked, what is the mass of an orange? What's your real answer? Well, not a great one. I mean, even in here, all of these different oranges have different masses. So what we can do is we can say this whole bag has, I can see 1, 2, 3, 4, 5, 6, 7, 8. There's probably one in the back, 9 oranges. And if it weighed 9 pounds in total, I could say the average orange is going to weigh 1 pound. Now, again, this is 9 oranges in a bag. However, we have millions and billions and trillions of atoms in a small sample. So if I'm taking a large amount of those, a larger sample, as you may know, is more accurate. And so if I have that available to me, then wow, that can give me a much better idea of the mass of an atom, no matter what isotope it is on average. Our periodic table uses these weighted averages, and they become percentages based upon what we've seen on this planet. So this planet is different than another rocky planet that we found in a different solar system because it has a different accumulation of those different atoms and those different isotopes. So on this planet, which we're on, we're going to be utilizing the periodic table and its values, because if we were on a different planet, same periodic table with elements, but the masses would be probably quite different based upon how it congealed together from stardust. So let's just take kind of an example of what we have when we look at this. So this is a graph of what comes from the mass spectrometer. A couple little things here. You have a mass to charge ratio. Z is charge, M is mass. And we see that the relative abundance, so this can be seen a couple different ways, as you'll see throughout this whole section. Relative abundance means a comparison. So if there's 100%, there's not 100% of what would be called boron 11. What the idea is that there's a comparison. It looks like about 20-ish% or 20 out of these compared to 100. So in comparison, it's a relative abundance. That's less important. What this is really meaning is a lot like our oranges. We have a lot of oranges in one mass and a few oranges that are a little lighter. So, but if suppose you had 123 typical atoms, 23 are boron 10, 100 are boron 11. The total masses, so you total it up, divide by the average, and you get roughly 10.8, 3 significant figures because you have 3 here and 3 here. Don't worry, significant figures are only worth 1 point on the entirety of the AP test. So it's a very small amount, but you want to try to be as accurate as you can. Now that means 10.8 is relative atomic mass of boron, which makes sense. There's more 11 than 10, so the average is going to be closer to 11 than 10. Let's take a look at some other examples. So again, relative abundance, you sometimes have no axes on the y, no increments. And you can see that this one's kind of a 3 to 1. It's 3 times as high. So we would expect chlorine to be closer to 35 than 36, because there's a little bit of 37, but it'd be closer to 35. 35.45 is where it's at. You also have something like magnesium with its 24, 25, and 26. You can see there's a huge amount of magnesium. However, you do have heavier amounts and a good sizable amount, which for magnesium, it's going to be around 24.3, I believe, off the top of my head. So the idea is that you can see by looking at this, you can gauge what this would be. Sometimes they give you no values at all. And so you really have to estimate where this would be. So for example, like this one, you have the lowest 154, you have the highest 160, which would mean in the middle would put us 157, okay, which is a sizable amount. You can see this half kind of cancels out this half. You can see this area over here, which is lighter, is kind of going to cancel out this amount over here. So the factors that, in trying to understand this, it's probably around 157. I'm going to edge that it's going to be on a little higher side because there's a pretty strong amount of 160, which again would have to be canceled out by a pretty strong amount of 154. But this is what you'll do on the AP test, be able to look at data and be able to interpret it and be pretty accurate based upon the mass spectrometry spectroscopy printout. Let's look at where mass can be very useful when we think about usually with compounds. So mass percent, the percent of mass, is used like any other conversion factors. So for example, when we think of silver nitrate, AgNO3, we want to know how much silver is actually in the compound because it's not all silver. So we take the mass of just the silver component over the mass of the total, just as like any percent, what you got on a test over the total, times by 100%. We see this is 63.498%. So what this is useful for is looking and actually using it as a conversion factor. Now, we can take any kind of compound and put it over 100 grams because this divided by that times 100% equals that percentage. So we use this 100-gram strategy to say if I had 100 grams of my silver nitrate, I'd have 63.498 grams of silver. So how many atoms of silver are found here? Again, some more examples of conversions. Have my grams. I have so many grams of silver nitrate for silver. This amount of silver gives me 1 mole. 1 mole gives me atoms, Avogadro's number. So I have this many atoms of silver in 0.35 grams of silver nitrate. Different elements will have different ratios, same ideas though. And again, if we had silver chloride, it'd be a different amount of silver in that one compound because they have different molar masses and different ratios. But this is another conversion factor we're going to throw in and use to our heart's content. Let me know what questions you have. I'm here to help. Take care.